طيب بسم الله الرحمن الرحيم. So in the first lecture we talked about the motivation for wireless communication in general. What are the applications of wireless communications that spans every aspect of our life, and why wireless communication deserves a separate study, particularly compared to wired networks, and what are the properties that distinguish wireless communication from wired networks. Today we're going to start with some historical background about wireless communication. Basically, wireless communication started back in like 150 BC or something like this, when people started to use light for communicating, like simple words and stuff like that. Of course, the foundation of microwave communication, where the communication relies on microwave signals, started in 18th century. The foundations have been developed or invented by Faraday and Maxwell, where they have started the first basic concepts about how to use electromagnetic waves for communication. طبعا in recent history.
Can you please explain to me what's so special about the microwave signals?
Microwave signals talks about electromagnetic waves, okay, that have certain patterns that dissipate in the air, right? People before 18th century, they did not have any idea about what is the microwave, how is this electromagnetic waves can be used for any type of communication. They did not have any perception or understanding about this. So Maxwell and Faraday were the first, early scientists who started to talk about these electromagnetic waves and how we can use them for any type of communication. طبعا, initially, people have been, communicating first and foremost using voice. We did not have the luxury, or we did not have the perception to send each other data or email or something like this. So in the early days, the main objective of any type of communication was first and foremost using voice. So people, they know how to communicate using voice and face-to-face. So the idea is that how we can allow people to have voice communication even if they are far away from each other. So this was the first, objective. In the past, when they started to put the first steps towards using concepts of networks and communication, we had, systems or networks that have been built with one single objective. As you will notice here, is that, in the early days, we had the telephone lines, مثلا. Telephone lines, maybe I'm talking about landlines, not mobile phones. And so in general, I think you will have some hardship because many of these, steps in history, you were not born, so you did not have the chance to experience these things. But in the early days, the first network that had been built with the objective of voice communication was landlines. Okay, so we had to build, switches, big switches, and dig lines and stuff like that. So typically, these types of networks were built with one single objective. So we need to build a whole system for one single objective. Of course, nowadays we're talking about, systems and networks that converge and provide all types of services that we can see nowadays. But initially, we did not have the science or the knowledge or the invention to allow networks to provide all these diverse set of services. So landlines, they were built with the objective of voice communication. In the early days, they started also to use TCP/IP and stuff like that to allow people to use a data communication, right? So, and that was also, through some wired networks, okay? So this was, revolutionary at that time. in wireless communication, we need to provide means for people to communicate, right? But without any kind of point-to-point wires, right? So this is the whole idea. Because wireless, as we said before, it provides portability and mobility, right? So we need to have this. So in the early days, in recent history, we started to see some early generations or early standards of wireless communication. Started with G1 or the first generation of wireless communication. And that was completely analog. So this was done in the United States, and it was in 1983. That's when the early, first generation of wireless communication happened. It's called the American AMS, or Advanced Mobile Phone System. It was completely analog, and what that means is our voice is inherently analog signal, right? What is analog signal? What it means, right? So analog signal takes infinite values in Y and X in time and in amplitude, right? So this is the analog signals, right? Our voice inherently is analog signal. So our voice is analog signal, right? Analog signals are easier to deal with. Why? Because simply, so analog signals talks about a signal like this. So this is an analog signal. So it has infinite values in the x-axis, and it has also infinite values in the y-axis, right? So if you look at it from x-axis or y-axis, they have infinite values, right? In the past, it was easier for scientists and developers to deal with such signals, because these are, it can be dealt with from physics point of view. They can deal with this using filters, and we had analog filters and stuff like that. The most important feature about these types of analog signals, as we will see later, is that the analysis of such signals in the frequency domain was quite easy, right? Hence, dealing with such signals using filters and stuff was so easy. Okay. In contrast, digital signals, which started in generation 2, as we will see, they talk about finite values, right, in the y-axis at least, in one axis at least, right? So it has infinite number of values in the x-axis, but in the y-axis they have finite values. They can take only discrete values, right? What's challenging about these types of signals is that using Fourier analysis, or I'm not sure if many of you have studied Fourier analysis before. We'll talk about it a little bit, and for those of you who have taken at least Network 2, they know what Fourier analysis are. So using Fourier analysis, these types of sharp transitions in the signal, they cause infinite components in the frequency domain. Okay, so if I were to convert this into a frequency domain, usually I will end up with infinite components in the infinite frequency spectrum, right? So in the early days, this was quite challenging. They did not have the perception how to deal with such digital signals. So, but analog signals, it was the standard, the de facto standard at that time, and that's why in generation 1 they started with analog signals. So all the walkie-talkies and all these devices in the past, they were actually using analog signals. That's it, right? So so we understand the difference between analog signal and digital, and what's challenging about digital signals. In 1991, the European Union, or the European countries, they started to talk about the first digital standards, the first ever digital standards. And the workaround that they did to try to get around these types of challenges is that they use signal approximation. So if you convert this signal into the frequency domain, you have infinite frequencies. So they usually use filters which transition in the time domain as approximation of this signal. So they always use signal approximation, right? But they have proven that this signal approximation is quite enough for our communication, and the voice quality and all the qualities that we need are preserved, and that's good. Okay, so they started to deal with this using some approximations. And of course, again, the Fourier analysis helped a lot in that case, because they have proven that discrete signals, they have infinite components of frequency, but they have finite number of frequency ranges in the frequency domain. We'll talk about this. So at least these finite number of frequency components, it allows them to use some filter and stuff like that, and that would be enough approximation to deal with that signal. In any case, so they started with the first digital standards, okay? So in digital standards, the European, they implemented the DICT standard, which stands for Digital Enhanced Cordless Telecommunication. And that was used mainly for cordless phones and these types of things. So what's distinct about this is that this, when I talk about 1880 or 1900, that talks about the carrier frequency. Carrier frequency here talks about the fact that, of course, in the frequency domain, when it comes to wireless communication, we have two types of communication. We have what we call baseband communication, and we have broadband communication. So this is the frequency. So when we, for example, our voice, does any of you know the bandwidth of our natural voice, the actual bandwidth or the width of frequency for the voice?
Up to 20K.
20K ده حتى ultrasound. 4K بس. 4K بس. Above 4K is ultrasound. Our ears cannot distinguish above 4K. So when we talk about using مثلا a voice signal, and we communicate voice signal over wire, like for example twisted pair, we usually actually, this is what we used to use for landlines مثلا. So we usually use what we call baseband communication, which means that the signal itself has a bandwidth of 4 kilohertz, right? So we deal with the signal in the zero frequency, yani the signal itself has some zero frequency components, right? In wireless, we cannot use baseband communication. Why? Why? Can anyone think about why? Because of interference, right? Because if we transfer multiple signals in baseband, this means that these signals, they will overlap in the air, because the air is shared. What's good about wired networks is that everything is guided. So the signal is traveling in a guided medium, right? But in wireless, we cannot use baseband. We cannot, right? So we have to use what we call broadband. So in broadband, we have to control shifting this signal in a specific frequency range in the frequency spectrum, right? To try to avoid any kind of interference. So if I have two signals and I shifted these two signals in two distinct frequency ranges, they cannot overlap in that case. Or they may overlap in time domain, but in frequency domain they are separate. So this means I can distinguish one from the other using simple filter. I can filter as a signal in the frequency domain, I can deal with them easily. So this is what we call broadband communication, right? So whenever we say that this is 1880 or these types of numbers, this refers to the carrier frequency, where the signal is actually shifted using broadband communication in the frequency domain to be able to deal with it in a frequency spectrum that does not have any kind of interference. واضح كده؟ So they actually standardized DICT standards in this frequency range in 1880 to 1900. Within that frequency range, they divided the big, this range into 120 channels, right? So a user can use a channel to communicate at any point of time, So these channels are separate and they cannot, خلاص, there's no interference between them. But this means that in a geographical location, I can have up to 120 users communicating at the same time in one geographical location. That's maximum. This is the maximum, right? Starting the digital was actually a big revolution. Why? Because in digital we can easily start to talk about data communication as well, which did not exist in analog communication at all. By data, I mean that in addition to our voice that we use for communication, we can actually transfer to each other some words, text, emails, things like that. So that started only in 1991, okay, with the DICT standard, right? واضح كده? So this DICT standard supports 100 to 500 range. And what that means is that the nodes, they can transfer using a power in that frequency range. And as we all know, the signal, when it travels to the, through the air, it suffers what? Suffers attenuation, right? So until a specific distance, it dies completely, which means that if you have any receiver above this range, you have no signal whatsoever, right? So that's what this range refers to, is that above this range, I cannot communicate. In fact, this is theoretical range, which means that this is the vacuum, if you have communication inside a vacuum. But of course, typically, we have obstacles, we have towers, we have furniture, we have this and that. So the typical, range is, somewhere in between. It's not close to 500. واضح كده? So this type of data traffic, 1.2, it was طبعا a big revolution at that time, but you need to know that this is the aggregate data rate for all the 120 channels, not for one single user. So if you divide this by the 120 channels, the data rates per user is quite small. But at that time, it was big, right? Of course, nowadays, we enjoy high data rates and we can download, high definition videos in no time. But of course, in these early days, it was quite an achievement. So in addition to this, they had defined some application layer services. So with the digitization, now we can talk about a voice encryption. So now we can talk about voice encryption because we have digital data. In analog, how can you encrypt analog signal? You have to convert it to digital in order to encrypt, صح? So we did not have this, even security was a big issue for analog, communication. But when we talk about digital now we can use data encryption, we can use authentication, we can use some application level services, right? The user density was 10,000 users per 1 kilometer. So which means that you can have up to 10,000 users in 1 kilometer square communicating at the same time. But that doesn't mean that all of them are using active communication, because these 10,000 users, they will share the 120 duplex channels. So you can have concurrent communication from 120 users. But this number is the statistical density. If you have this number of users, statistically at one point of time, you will have maximum 120 users having active communication. Okay? And others are in an inactive mode. Okay, واضح كده؟ طيب. So GSM or second generation, GSM was quite a revolution was a huge event or what they call global system for mobile. This also started in Europe. And the big difference or the big advantage for GSM is that this is the first standard where we started to talk about what we call user handoff. And this was big. Why? Because with DICT, if you move, we talk about the basic advantage for wireless is mobility and portability, right? But if I talk outside the room, right, and there is no actual communication for one node, I cannot hand off to another base station or to another, access point or whatever. خلاص, I lost communication. Even if there is access point in the next room. We did not have any way of providing handoff. Like right now in the university, I can start to have a phone call, right? And I can move with my car inside the university normally, and I can hand off. I don't even feel it, right? And I don't have any service disruption, right? In the early days of DICT, that did not exist. So if you move a few meters, you lost communication. That's it, right? So GSM not only supported the handover, they supported even roaming, which means that you're not even handing off from one base station to another, you're handing off from one country to another. Even if you travel, at least within Europe, you can still have communication and service, right? So you can drive your car freely in any country in Europe, and you can still have communication, right? So that started with second generation or GSM. It was fully digital at that time because this one was hybrid, supported some digital and analog, but this one is fully digital. We started to talk about fully digital بقى خلاص. We moved everything to digital domain, and now we can, because we know how to deal with it now. So we have 124 channels, and this works in this carrier frequency. This is the center frequency, the center carrier frequency. We'll talk about, in a few minutes, we'll talk about what is the significance of these carrier frequencies. This is quite important because in each of these carrier frequencies, you have specific properties for the wireless signal that we need to understand really well. What's different about using this 900 megahertz, and now we talk about 60 gigahertz, مثلا. Some standards do use 60 gigahertz. What is the implication of this? So we'll talk about this. In addition to roaming and handover, and that actually required the use of, or the implementation or the support of automatic location. Automatic location here talks about the fact that I can locate any wireless nodes and know where they are, at least within a cell boundary. I don't know the exact location, which means latitude and longitude. I don't have to do that, but at least I can know where geographically this node is. We did not have that before. Before that time, we did not have that. I don't even know the location. So now I can know through the wireless signal, internally, through the handshaking between this wireless signal and the base station, I know exactly where the location of that node is. And what that helps me to do is that I can route phone calls accordingly. I can do some data services based on location. We started to talk about location-based services because I know the location of that node and so on. So roaming was also supported. So we know the difference between handover and roaming, right? Handover talks about roaming within the internal. Handover means that you move from one access point to another, but within the same system or the same city or the same country. But roaming here talks about the fact that you transition from one carrier to another carrier completely. From one carrier network to another carrier network. So from Ooredoo to Orange in Europe. خلاص. This is a network and this is a separate network altogether. ماشي كده؟ So as you see, this is the data rates per user. So 9.6 bits per second. تخيل انت فمش k bits per second. So طبعا data rates was quite small, but this allowed us to have at least some services like fax, like emails, things like that. Some basic data services. So as we said, the cellular communication was built with the objective of mainly supporting voice communication. Mainly. Data service came after this, right? And why is that? Because they started the cellular communication or terrestrial communication with the objective of voice. So the network itself is built around the concept of circuit switching, right? So we talked about circuit switching and packet switching, right? So with circuit switching, before doing any communication or any service, you have to establish a virtual circuit first. So establishing the virtual circuit takes time, right? But why do we do this? Because establishing this virtual circuit will provide a dedicated medium for this particular communication, and that ensures quality. صح كده? And that's why when we talk about voice communication, we always get charged by the second. صح? We always get charged by the second, right? Even if you are not even if you're not saying anything, and if you call someone and then put the phone aside and walk away, you're still getting charged, right? Even though you're not communicating, you're not saying anything, but you are consuming the circuit, right? So the circuit has been established, has been dedicated for you, right? Unlike data services, when we talk about data service, we always get charged by bytes or kilobytes, or okay. So if we're not using the data services, we're not getting charged, right? Why? Because in data services, we're using packet switching, right? So you are consuming resources only if you send packets. If you don't send packets, you're not consuming anything. This was a fundamental difference between the two. So wireless communication, generation 1, generation 2, up to this point, was actually targeting circuit switching. It was built around the concept of circuit switching, because of the fact that the main objective was voice communication, right? Not actually data. Even data, we try to tweak circuit switching, right, to provide some data services. But the network itself is circuit switching, right? This is in contrast completely to wireless LANs. When we talk about Wi-Fi standards does not follow G1, G2 كده. Wi-Fi standard is parallel standards, but we're trying to talk about it because in chronological order, we need to talk about the overlap between the two. Why? Because wireless LANs, they started with the objective of data communication, not voice. So in the early days of wireless LANs, we talked about wireless LANs only to provide data, because we have already cellular communication or wireless communication for voice. So in the early days, this is for voice and this is for data. واضح. Okay? So wireless LANs, they were built around the packet switching concept. Okay? So in data link layer, we talked about this. We talked about Cisma CA and so on and so forth. And this was all built around packet switching. We're not establishing, we never talked about establishing a virtual circuit or a dedicated circuit for the case of wireless LANs. Never talked about this because it's built around the packet switching concept. Why? Because it was built with the objective of data. Okay? Type. So in parallel to the generation 1 and generation 2, in 1997, they started to say, okay, so we know how to provide data services, a little bit of data services on top of the circuit switching network, like GSM, but we need to have a standard which is built around data services. ماشي? So they started to talk about a completely separate standard. اللي هي بقى started with 802.11. First started with 802.11 B, and then G, and then later on N and AC, and now we're talking about a new standard AX, okay, and A and E, and يعني there are so many standards in that category, 802.11, okay. So that started in 1997 with the first standards of 802.11. The standard بقى, they started to use برضو 2.4 gigahertz. So again, we'll see why, because we know nowadays that the range of mobile communication مثلا, or using 5G or something like this, the range is always much larger compared to Wi-Fi, صح? We know that, right? So even the towers, they can be like 500 meters away or even more, right? But when we talk about Wi-Fi, we cannot increase the range above 100, right? Why? Because of the fact that in the frequency ranges here that we're talking about, together with the power of transmission, they both define the maximum range that you can get to when it comes to communication. Okay, we'll elaborate on this in a little bit. But in 802.11, they started with carrier frequency of 2.4. And the attraction or the reason for this is that this is what we call a ISM band. ISM band is a free licensed band. ماشي؟ اللي هو بيسموه industrial مش عارف ايه medical حاجة زي كده. ISM band. ISM band is a free band, which means that if a carrier manufactures device or a vendor manufactures devices that use this carrier frequency, they don't have to pay. They don't have to pay money to the government. Okay. Unlike other frequency spectrums, which require licenses, and they pay usually millions of dollars to license this frequency spectrum, because there is very tight regulations when it comes, as you can imagine, very tight regulations when it comes to frequency planning. So 2.4 was free range that attracted many, vendors and manufacturers to start, promoting devices in that range. And it becomes now, طبعا, it becomes more and more crowded, and that's why, we started to have many interference issues in that particular band. Okay, so we started to have the first standards of 802.11, and that had only a theoretical bit rate of 2 megabits per second. And this was the B standards. In G standards, we upgraded, mashallah, to 11 megabits per second. Now, this was huge at that time. Of course, now we are getting into 3-4 gigabits per second, easily. Okay. So, as we said, wireless LANs, they start with the objective of data communication, right? And it goes really in overlap with the generation 1 and generation 2. In 1998 بقى, هنا, pay attention to this. In 1998, we have the first specification for a GSM successor. So what happens here is that the IMT 2000, which is part of ITU, they started to put some requirements specification. So we need to have the next generation after GSM. So GSM was promoted worldwide, and it was a predominant in standard. But in terms of data services, it was quite primitive, right? So we need to provide more data services. We need to have high data rates and so on and so forth. Okay. So they put the IMT 2000, which is the set of specifications of how they want the next generation standard to be. And it took, as you can see, it took from 1998 all the way to 2001 until this specification has been implemented in actual wireless nodes that people have started to use. And that's normally how the process goes. First, the standard body, they say, okay, so we need to have some requirements for the next generation wireless, okay? So they put this to the vendors, and then the vendors, they start to put some, experimental prototypes to say, okay, so I can fulfill all these requirements using my device. And they start to have some struggle. I have more data rates, you have more quality, I have more efficiency, you have this, you have that. And then they reach some consensus, and then they put together one standard that meets the requirement, and it has all the details about how these wireless devices should be implemented or developed. And then they start to deploy these wireless devices in public, and people start to use it, and that usually takes a few years. And that's exactly what we are in when it comes to 5G. Now, we live in 5G era, okay, but of course, we are starting to talk about 6G, okay? 6G maybe in 10 years from now, we will start to have some deployment, but now we have some deployment for 5G. And even 5G is not fully deployed. 5G until today is not fully deployed. واضح? You can follow up so far? So one of the proposals was UMTS, or Universal Mobile Telecommunication System, from the European side. The European Union, from early days, they believe a lot in standards. They are naturally كده based on social systems, so they believe that people should be unified, and we should have standards that everybody uses. The American system is market driven, and usually that leads to many proprietary specifications that many manufacturers, they start to use, and they build some proprietary devices, right? And then later on, they adopt European standards, or they adopt their version of the European standards. But the market competition in the US is furious, and based on that, they start to have many implementations and proprietary stuff, and just to cope with the competition in the market. European, they take it slow, and they start to talk about, they take their time in developing standards, and they come up with it. But now, of course, people started to believe more in standards and interoperability and so on and so forth. And of course, with the complexity that we have in life, we need to have some interoperability between vendors. So in any case, so this talks about the specification for the GSM successor, which was dominated, or the proposal that dominated this was UMTS from Europe, right? So UMTS was the first proposal, which have been realized in 2001 as the third generation wireless. Okay. But in the meantime, the standard developers, they were saying nothing would stop us from working also on data services on top of circuit switching. And that was quite a tweak, right? So they started to talk about some standards that uses circuit switching for data services and increasing the data rates. Why would they do this? The reason mainly was the fact that in 2.5G, we started to talk about some incremental standards on top of GSM, like high-speed circuit switch data. This did not exist before. So they started to say, okay, so we can increase data rates on top of GSM network, right? So that they عارف احنا بنسميه حل شوية ترقيع instead of going into a full deployment of hardware and software and cost operators hundreds of millions of dollars, because this changes the system completely. You have to deploy hardware and software, and everything has to be replaced, right? So this is a revolutionary approach. In 2.5G, they started to talk about evolutionary approach, okay? So let's see what we can do with what we have now, right? So this HSCSD, or high-speed circuit switch data, was just a software upgrade on the servers. That was it. So if you update the core network servers with some software patches, you can provide this data service, and that provides a 57.6 kilobits per second per user, which was quite an upgrade, of course. When we talk about 9.6 to 57, this was quite an upgrade, right? GPRS بقى was the first packet-oriented data services on top of GSM. GPRS برضو, it was big event at that time, because developers, they started to talk about how to tweak circuit switching to provide packet-oriented like service of data. This was GPRS. But again, with this, we cannot increase data rates that much. As you can see, it's comparable. But at least it's packet switched, which means it gives the operator the ability that they can charge users by packets, not by seconds. Okay? So this was also quite an upgrade. This is cost efficiency. From the operator's point of view, this is cost efficiency.
And why the reason of the speed decrease a little bit?
Right, because they tweaked circuit switching to provide packet-oriented data. So,
The same hardware.
yes, with the same hardware.
Yeah.
So to do this, there is quite an overhead, right? So the bit rates did not improve, but at least they can provide packet switching, like packet switching, like it still uses circuit switching network, but it provides packet switching like behavior to the user at least. ماشي? So this was what we call a 2.5G, and we have, by the way, 3.5G. We have 4.5G. Because the generations, they talk about big milestone in the standard development, right? But in between, we have some incremental, incremental upgrades and incremental specification development, which sometimes they refer to as 2.5G or 3.5G or 4.5G and so on. Okay, and I'm sure there will be 5.5G. ماشي كده؟ طيب. Third generation بقى اللي هي UMTS طبعا. يعني هنا I'm talking about mainly UMTS. We'll study all of these, by the way, in more details later. Here we're talking about some historical and chronological steps in terms of wireless communication standards. But we'll talk about each of these generations in more details later. Third generation was first deployed back. It was developed, of course, early on, but the deployment was done in 2001, right? Third generation, it talks about CDMA. CDMA is, some of you know, code division multiple access, right? CDMA is a way of providing some multi-user communication. So some of you know that. We'll talk about this. Don't worry if you don't know what CDMA is. We'll talk about it in more details. But it's a way to provide concurrent communication between multi-users, right?
It's comparable to GSM because
La. GSM talks about a network, right? CDMA talks about multi-user communication. So if two users talk at the same time, right, and at the same frequency, what will happen? Interference or collision. In wired, we talked about collision. In wireless, we said that we cannot detect collision, but there is high level of interference. But in both cases, we cannot have communication. صح? But if we talk about two signals that talk at the same time but at different frequency, it's fine. When we talk about signals that go at the same time but uses different guided medium, it's fine. There will be minimum interference, but that's fine, right? CDMA بقى talks about neither. Two signals that work at the same time, at the same frequency range, but they do not collide. Using بقى ايه؟ الطاهر؟ اوكي. Using بقى ايه يا طاهر؟ عشان انت من electric engineer. انت you will be our reference بقى. When two signals they go at the same time and at the same frequency, but they do not collide using CDMA. Using بقى ايه؟ CDMA uses ايه؟ اللي هي الايه؟ لا uses orthogonal codes. اللي هي الchips. We'll talk about this. We'll talk about this later. يعني we'll talk about this يعني. Don't worry يعني. But in any case, of course, in third generation يعني كان الناس اتهبلت بقى. يعني ايه ده؟ يعني the CDMA يعني I can have the same signals, multi-user communication at the same time, at the same frequency, and the signals would not interfere. This was revolutionary at that time, right? So this way they were able to increase data rates much higher, right? Yes. So UMTS was quite a revolution. Was based completely on CDMA. Second generation was based on what? FDMA. هو using broadband communication. So users, they can communicate at the same time only if they have different frequencies. This is the only way of providing multi-user communication for us. اللي هي broadband communication. But CDMA talks about multi-user communication within the same band at the same time. So we'll see how this happens. And of course, nowadays we're talking about starting from 4G بقى و 5G, we have what we call بقى OFDMA. OFDMA, orthogonal frequency division of packages. So they switched from CDMA to OFDMA. So at the beginning, they were really impressed with CDMA and how CDMA can provide high data rates. But in a later stage, they started to talk about issues, which we will cover in the course in details. And that's why in fourth generation, they started to talk about completely different way of multi-user communication. And that was also a revolution. Since then, by the way, until today, there has not been any other way of increasing the frequency spectrum or increase spectrum efficiency or data rates since OFDM. And that's why people started to talk about the fact that the development and the evolution in the physical layer has stabilized completely, because people have reached some level of physics that they cannot increase data rates above this. خلاص. We cannot increase data rates above this. So we forget about multi-user communication paradigms, and we started to talk about some other issues. We'll talk about them, like carrier aggregation, like the millimeter waves. They start to talk about other issues. But خلاص, OFDMA was a huge upgrade, and since then they have not been able to provide anything better than this. So CDMA 2000 was the standard in US and Korea that aligns with UMTS in Europe. So UMTS was the standard in Europe. CDMA 2000 was the standard in US and Korea. واضح كده؟ ماشي؟ CDMA 2000 here refers to the multi-user communication paradigm, which was in the name of the standard. But UMTS talks about the standard in Europe, right? But it still uses CDMA. ماشي كده؟ واضح كده so far؟ طيب. So switching back to wireless LANs, in 2002 we started to also talk about handover in wireless LANs. This was actually برضو a big step in 2002. So here we talk about wireless hotspot. They started to widely spread. Okay, and now you can deploy wireless hotspots, and you can hand over from one to another seamlessly, right? We did not have this before. ماشي؟ طيب. Also there was the standard for WiMAX. WiMAX was the another European standard that started to emerge. But WiMAX died completely after. It was a big revolution at that time. They said that okay, so WiMAX is the one that will dominate, and GSM will vanish and stuff like that. But what happened was completely the opposite. WiMAX died completely. So we don't have to talk about the details of WiMAX because it lost ground completely to GSM, and later on, of course, to UMTS. طيب. In 2006, we talked about, they started to talk about 3.5G. Again, this is an intermediary step before 4G, which was completely based on OFDMA, the fundamental communication paradigm. So 3.5G would talk about still using UMTS, okay? Still uses CDMA قصدي. But we started to have high data rates using what we call a high-speed downlink packet access. So they said, okay, so we have UMTS, which was based on CDMA. So they started to talk about high-speed downlink data access. So why we increase the data rates for downlink, but we didn't talk about uplink? Because basically, people, usually consumers like us, we always work in the client mode. We always consume data. So we always like to have download speed much higher compared to upload speed. And this is the case for ADSL. ADSL was based on this notion. ADSL talks about asymmetric digital subscriber line, right? Asymmetric here refers to the fact that the download speed is much higher compared to the upload speed. Upload speed, you need it only if you work as a server, right? and that was not as common as consuming data services. So high-speed downlink packet access started in Germany in 3.5G, and they started to talk about data rates which is like 3 megabits per second. Of course, this is quite high compared to bandwidth, the data rates that we talked about before. ماشي كده؟ طبعا in addition to high-speed downlink packet access, they started to also standardize high-speed uplink. Uplink here talks about the fact بقى that ايه uplink معناها ايه from servers بقى up. ماشي؟ They also started to talk about increasing data rates for this, and this was actually for good بقى for enterprises, companies that want to use some server mode services. تمام؟ In 2010 بقى we start to talk about 4G. 4G they is based on the notion of long-term evolution or LTE. LTE they called it long-term evolution يعني very بقى ايه futuristic يعني. And this was based on the fundamental communication paradigm of OFDMA, or orthogonal frequency division multiple access. And what OFDMA tries to achieve is that in FDMA talks about the fact that I will explain in basic terms now, but in a later stage we will explain it in details. So in FDMA, all what we can do is that we can provide channels with some guard bands between them, right? So if we have a specific bandwidth, like مثلا 20 megahertz, and we can divide it into sub-channels with some guard bands, so you can imagine, you have some limitation of the number of channels that you can have, which means that you can have limited number of concurrent communication happening, usually very few, right? So in OFDMA, not only did we remove these guard bands, we started to talk about channels like this.
They can collapse with those.
Yes. They have significant overlaps, and we can still distinguish these signals from each other. So how can we do that? We can do that only using the theory of orthogonality. So that's why it's called the orthogonal frequency division multiple access. ماشي? This orthogonality means that despite this overlap, but as we can see, the peaks exists with the zero frequency of the next one. So I can extract the peak because the one after it has zero frequency in that case. So this allows the implementation of special filters to try to extract these signals from each other. Of course, as you can see, this is revolutionary, right? Because in the same bandwidth now I can squeeze at least 10 times the number of channels. صح? Not only that, but we'll talk about orthogonal frequency division multiple access. These channels I can assign to different users. ماشي? Which means that I can have hundreds of users having concurrent active communication in the same geographical area. This was the revolution that led to data rates that we enjoy today. And since then, there has been no other revolutionary paradigms after OFDMA. Okay, that's why 5G did not change. Was also based on OFDMA. Okay, 6G. They have not, at least as far as I know, until now, they have not talked about any other communication paradigm other than OFDMA. So the development in the physical layer has been quite limited.
Professor, we had this before in the 3G. So what was new in the fourth generation exactly?
ما بقول لك ال OFDMA. They completely replaced CDMA خلاص. CDMA was completely replaced from the physical layer, so that requires huge amount of upgrade and replacement of everything, right? In 5G, that question might be more valid in 5G, because in 5G, if they are not changing OFDMA, so what's new in 5G? There was quite a bit of new things, including بقى هنا including machine type communication, network slicing. All of these are not in the physical layer, with the only exception of massive MIMO. We'll talk about MIMO in a few minutes. MIMO here refers to multiple input, multiple output, right? So nodes usually they use one antenna, right, for communication. MIMO here talks about multiple antenna on the same node. So our mobiles here, they have at least 20 or 30. I don't know how many antennas in our mobiles, but يعني plenty of antennas. In the tens order of antennas, right? So 5G, they start to talk about massive MIMO, which means massive here refers to the fact that the number of antennas will be in the hundreds level, which means that you can have tiny little antenna in the level of hundreds, maybe 500 antennas or something like this, in a node, in one single node. And that gives us بقى some يعني data rates limit, which is not existing with the single antenna. We'll talk about why in a minute. ماشي? So with massive MIMO, with carrier aggregation as well. Carrier aggregation here, they said that, okay, so for one single carrier, we cannot have more channels above what OFDMA can provide us, but we can dynamically assign multiple aggregated channels to one single user, which means that one single user can enjoy instantaneously very, very high data rates. Okay? But we need to be smart in allocating all these channels in a very smart way. So one single user can have some, aggregated channels dedicated to that user in one instance of time. And then other users will be allocated these channels dynamically using some smart algorithms. That's why in radio communication or radio resource management, it's quite complex. And we'll talk about this in significant part of the course, how to do some radio resource management. It's a big challenge. Of course, each of these requires a lecture to just talk about. Network slicing, we're doing a lot of research in network slicing, at least in our group. Network slicing here provides end-to-end reliability and guaranteed quality of service from the node all the way to the core network. And it provides some virtual, on packet switching, we provide some virtual end-to-end channels that guarantees quality of service for certain category of applications, right? So that also exists in 5G, and there is quite a bit of research in this area. Maybe one of the students can give us a seminar about network slicing later. So each of these deserves really a special talk on their own. URLLC talks about ultra reliable, low latency communication. This is again special type of service which has been provided by 5G. Machine type communication which was designed for sensor communication in particular, if you have massive number of sensors deployed in the environment. So each of these deserves a separate talk. But anyway, these are all services that came with 5G.
In the term of the hardware, the newest generation hardware can also support the previous ones? For example,
to a very limited extent. So operators, they always talk about software upgrades because this is cost effective. They don't have to change hardware, data centers, and stuff like that. So from 4G to 5G, right? You can only achieve all the capabilities or features of 5G. You cannot achieve that using only software upgrade. Never, right? And operators who say or who claim that we have 5G network, right, using only software upgrades, they only can achieve part of the 5G specifications, but not full support of 5G. Never. 5G. But because, as you said, because both of them is based on OFDMA, there is a chance you can do some software upgrade and support part or subset of 5G features, but not all of them. يعني for starters مثلا microwave أو sorry millimeter wave. Millimeter wave talks about communication in 60 gigahertz or something like this. But يعني the current network that we have talks about يعني 1 giga مثلا ولا حاجة زي كده 1 gigahertz. So they start to talk about millimeter wave for specific reasons that this band is يعني is interference free and so on and so forth. It has some opportunities. So they talk about what when we talk about carrier aggregation as well. We talk about user channels in the millimeter wave as well as in the 1 gigabit range ماشي. And for the user they are aggregated seamless ماشي. But millimeter wave is not supported as far as I know يعني in the current network.
So
Millimeter. When we talk about why now.
Devices with the newest generation can support previous generations, but not personal.
Of course, they can provide all the services in previous generation, but they add to this higher data rates, different services that were not supported. Yeah, of course. Backward compatibility is always a requirement, by the way.
Because when you travel far away from.
Yes, of course, absolutely, yes. I did not understand the question at the beginning, but you're quite right. All the standards that we talked about are always backward compatible, right?
And also I have read recently, like in terms of support, like in Qatar, the devices that depends on the 3G systems will not be able to work. I have read this.
Okay, so yes, backward compatibility sometimes it has certain limits. يعني similar مثلا لو انت عندك تليفون مثلا and then you do some upgrade for the operating system. After certain limit you say okay, so the operating system يعني 10 times back is not supported. Okay, so same thing. Yes, same thing. So of course before they limit the support for third generation, they make sure that no networks on is actually still using third generation.
For example, when I come near the border, for example, I come to Saudi Arabia, the only support is 3G at that time.
Right.
Yeah,
Right.
that was
Right.
the issue.
But the backward compatibility is a big issue in any standard طبعا. It has to be backward compatible. So sorry we took too long. Of course this here talks about يعني so again this is part of the motivation. I should actually remove this or move it to another to be part of the motivation. But what we can notice here is that يعني pretty much everything is increasing, but there is when we talk about active mobile fixed telephone lines, we see that the fixed telephone lines started to decrease. Everything is increasing, but fixed telephone lines they started to decrease, and that makes sense. I mean, people started to rely less on telephone. So some of us we don't have landlines anymore. Actually, most of us now we don't. I still have one, but يعني, most of us we don't have landlines. يعني. But this talks about the exponential growth of adoption for the communication standards that we talked about. So some of the important areas of wireless communication, areas of research in mobile communication. طبعا each of these areas they require again يعني elaboration and details and things like that. But we'll just give hint about what type of issues exist in each of these areas, and leave the details for later when we start to talk about the details of all these standards, and when we talk about modulation schemes, and this will become clearer and clearer. So the approach of the book is that first it gives you the whole picture, and then it provides more clarity in different parts. ماشي? Start talk about the details, but this is like the global picture. So we talk about transmission quality and spectral efficiency. So when it comes to spectral efficiency here, we talk about the fact that if we have a communication bandwidth for a specific carrier, actually this is whether baseband or broadband, we'll talk about we have a frequency spectrum range, ماشي? And we need to use that for communication. Okay? Spectral efficiency here talks about what is the ratio between the maximum data rates that we can provide given this bandwidth divided by the range of frequency. Okay? So for example, if I use this bandwidth using FDMA, ماشي, and using one single antenna, and use this specific transmission power and I can reach to a spectral efficiency of, let's say, 10 megabits per second divided by 20 megahertz. Okay? So this means I can have this spectral efficiency. Of course, CDMA, as we can imagine, provides more spectral efficiency. So I can, using the same bandwidth, I can reach to higher data rates, which means more spectral efficiency. Okay? OFDMA gives even more spectral efficiency. So I can increase the spectral efficiency using multiple ways. Fundamentally, I can change the multi-user paradigm, communication paradigm completely. ماشي? Or alternatively, I can increase the transmission power. Transmission power reduces اللي هو error probability and so on and so forth. I can reach to higher data rates and so on. So spectral efficiency is maximized. I can use multiple antenna to increase spectral efficiency and so on. Okay, so I can increase spectral efficiency using multiple factors, and it's up to the telecommunication designers to decide what is the design of the transceiver of the wireless node so that I can reach to a high spectral efficiency with minimum cost, with some limitation on power, and so on and so forth. So that's a big area of research. Modulation here talks about إيه؟ Modulation talks about broadband communication. ماشي? And we'll talk about modulation schemes a lot in the coming lectures, inshallah. So within the broadband communication, how can I transfer back communication symbols, and what are these symbols? We'll talk about this. And of course, coding, when it comes to coding, what is the actual codes that I use? We talked about this in Network 1 a little bit. We touched on this a little bit. We said that all these symbols, we convert them into codes, and the codes are, they have to be error protective, and they have to have some resistance to errors, and so on and so forth. Interference, of course, we all know it. Radio resource management is one of the most important area of research in wireless communication. 90% of researchers, they work on radio resource management. So radio resource management, some people, they talk about it from the perspective of multi-user sharing one base station. How can I allocate the radio resources? Radio resources here are what? We have multiple antenna at the base station, multiple antenna at the user. We have frequency ranges, we have channels, we have in OFDMA, we'll talk about something called resource units and stuff like that. So all of these, for me, are resources. ماشي? So I have a huge pool of resources at the base station side, at the user side. How I can allocate these resources in such a way that guarantees that the users will have the maximum quality and the best service, quality of service, okay? And at the same time, it maximizes the utilization of the network from the operator's point of view. Because if I allocate lots of resources to a user and the user ends up not using these resources, it's a disaster, right? Right? For the operator, this is a waste of resource. ماشي? But there is they start to talk about using machine learning and using machine learning for radio resource management, and even using LLM. Abdurrahman will give us some idea about this today. So machine learning can implicitly predict if the users, they need these resources or not. So there is some probabilistic factor, and that's why this is the most challenging part of wireless communication, radio resource management. Let alone if I talk about it from an end-to-end perspective, which means that I include the resources in the core network as well. You have servers, and these servers, they have CPU time, they have energy consumption, they have this and that. So if I allocate resources using certain pattern or certain allocation, it leads to energy consumption at the core network side. But if I rearrange things, I can reduce energy consumption, which means that I'm more green and environmentally friendly, and so on and so forth. There are lots and lots of issues, countless of issues when it comes to radio resource management.
What is the added feature in 5G that they claim that it is not good for human health? Nowadays they are saying that 5G is dangerous and
Right.
what is the added feature in this?
هو two things as far as I know. الحديث كتير قوي عن موضوع المليمتر wave and the effect of this when it comes to radiation on human. Because as part of 5G standards, there is a specific, very unique part talks about millimeter wave. ماشي? So when we talk about millimeter wave, it deserves a study of the impact of this on human health and so on and so forth. All of these are speculations, by the way. No one has, has proved with no doubt that it has some health issues. But there is some speculations. When you talk about millimeter wave, that's a whole spectrum, brand new spectrum. So what is the implication of this on human health? The other thing is that also there was no clear specifications on the levels of power, of transmission power for 5G. Because for 4G, people have been talking about or have been researching a lot when it comes to radio resource management, energy efficiency. So there was a huge amount of work on energy efficiency and green communication up to fourth generation. In 5G, they were expecting to see some specs about energy efficiency and limitation of transmission power and so on and so forth as part of the standards. I'm not sure if they have updated because, by the way, the development of the specification of these standards is actually ongoing. And if you look at the IEEE website and you see the standards, you will see release 1, release 1.1, release and so on and so forth. So 5G talks about 5G. They take a snapshot of the standard and then they say this is 5G, خلاص. But that doesn't mean in 5G is frozen. So there is 5.01 G, there is 5.02 G, there is 5.03, and so on and so forth. So the upgrade or the development of the standards, I had the last discussion I had with the standard people, they were talking about no energy efficiency specifications in the standard. And energy efficiency is one of the biggest factors because you're not limiting a manufacturer to use some transmission powers which are beyond certain limits that, again, it affects the health in a negative way. And imagine if this telephone line, if this mobile, it uses some transmission power which is really high, so the effect of radiation on the brain and on the health condition is, we don't know. We don't know if it might have some implications. But more importantly, I think the millimeter wave was a big factor يعني. ماشي كده؟ طبعا mobility and طبعا location dependent services, it's one of the hot area because if I know the location of the wireless node, I can even predict that okay, Abdurrahman is going into the mall and he's currently next to XYZ shop. Okay, so send them some ads about good items and something like that. So I can do some prediction, and based on that, I can provide some fancy services to users. Also, quality of service support here talks about the fact, quality of service here talks about the fact that I need to have some distinction between users. Why? Because absolute fairness is not possible. Okay, so absolute fairness is not possible. And it never leads to efficiency, right? Why? Because people are different. The service that they consume is different. So I cannot give the same resources to X user and Y user. So that's not actually efficient, right? But X user, he uses huge amount of services and he's very heavy in data rates and stuff like that. So I should really assign more resources to that user. So quality of service here talks about the fact that how I can rearrange the resources to give the best experience to the user. Best experience, يعني for someone really modest, يعني if you give him يعني 10 kilobits per second, he would be happy. Because all what he wants is just to send an email. And he would be satisfied. But another user, he would not be satisfied unless يعني he can talk about, he can watch high definition video with no disruption. So quality of service talks about distinction, but distinction here is not in a discriminatory way. يعني distinction here is based on maximizing user experience. ماشي? Talks about user satisfaction in particular. ماشي كده؟ واضح؟ طبعا portability and power consumption and all of this is also nowadays we started to talk about computing. يعني we started to again برضو converge communication resources and computation resources. In the past, they were like two separate domains. So communication people, they talk about radio resources and so on and so forth, but they don't care about CPU times. I don't care, ماليش دعوة. And I assume I have a server or a cloud, they would do the job for me. Okay? And people in the computing part, they never had to worry about communication resources. Okay? So if you join both, there is a great opportunity to provide more efficiency and more user satisfaction. One of the areas that they started to evolve nowadays is that with cloud computing, I can tap into computation resources as much as I can, as much as I want, right? But I just have to pay. In cloud, I can have a virtual machine dynamically that would do whatever I want, right? But I have to pay for it, right? So the problem becomes cost efficiency. So if I have these computational resources and these communication resources, what would be the energy consumption for the system and what would be the user satisfaction? This is a big research question, huge research question, right? So if I increase the computational resources, I will pay more. So how can I address the trade-off between energy consumption and cost? Oh, wow, big research question, right? Good luck بقى يعني to try to achieve this trade-off in a big system. Imagine بقى if you have a system of tens of these base station towers, right? Which means that you have huge amount of resources, communication and computation. How can you manage all of this to give user satisfaction, to address energy consumption, to minimize cost, and so on? ماشي. Any questions? We're getting into so many things, but يعني in a later stage it will become clearer. احنا ممكن نقف هنا ولا ايه؟ ولا تالي المغرب جدا صح؟ We can stop here. We can. So when it comes to wireless communication, whether it's Wi-Fi or cellular communication, we keep in mind إن هو we only talk about the first hub. The first hub is the only wireless part. Usually, the back end or the back network is usually wired. ماشي? So here we have base station towers, but the base station towers are wired together usually, or in some cases they use microwave links in very limited cases. يعني. But in most of the cases, base stations are actually wired to the core network offices. Okay, so here it's wired, and here it's one hub wireless. But this is where most of the issues are. Of course, there is quite a bit of research as well in the back end and core network. But most of the designers and the research is actually in this wireless part when it comes to all the issues that we talked about, MIMO, carrier aggregation, all of this is here. But the management of all these resources is done here, right? So all the allocation of the radio resources is actually performed here, right? The algorithm, the intelligence is done here. In terms of course, a reference stack, this is the wireless node. And the wireless node, of course, has all the stack layers, starting from the application all the way to the physical layer or the network access layer. When it comes to base station towers, usually we talk about only 3 layers, similar to any router or any Wi-Fi access point. It has these 3 layers, right? Now we start to talk about edge computing, which means that these base station towers, they are also smart, which means that we have some application layer here where base stations, they started to be more and more smart. So they do edge computing to manage resources, at least partially, and so on and so forth. So they started to be more smart. But this is the communication stack, which is similar to wired, except that this hub is actually. So when we talk about the different issues, we talk starting from the physical layer here. Starting from the physical layer, when we talk about physical layer, we talk about electromagnetic wave or analog communication. And in analog communication, we have to refer to interference and attenuation and refraction, diffraction, and we'll talk about this in a bit. But also modulation to facilitate the broadband communication, as we said. In data link layer, we start to talk about frames and digital signals, purely digital. So here we can talk about encryption, about multiplexing or multi-user concurrent communication, media access control. We talked about MAC layer in network 1 and network 2. In wireless, it's very distinct. It has lots of issues compared to wired. We talked about this in previous courses, and we'll talk about some of these issues here. And of course, the biggest chunk is radio resource management, as we said. In network layer, we talk about handover. Why? Because handover is to move from the range of one base station to another, or access point to another, or something like this. So this has to have like some big picture. So it has to come from the network layer, right? Because the network layer is the layer that has some end-to-end view. It knows exactly the location of the access point, and it can manage resources during handoff. Handoff, we'll talk about handoff in details. This is one of the most challenging issues in wireless communication and in different types of networks, really. And the main objective is how to do handover without service disruption. And to do this is not easy, as we will discuss later. And of course, in network layer, we'll talk about also device location and addressing and routing. We all know these issues here. This slide is a bit important, and this slide talks about the physical properties of the electromagnetic waves in the different frequency ranges. This is quite important. Okay, so what is the difference between wireless communication in low frequency range and in very high frequency range or in ultra high frequency range? Okay, what is the physical properties that makes communication in each of these frequency ranges quite unique? And this is the main reason, by the way, that we have multiple standards in wireless communication, because we can ask ourselves, when it comes to wireless, we know it's a wireless medium. Why can't we have one single standard that covers all of these communications? Why do we have Bluetooth and Zigbee and Bluetooth low energy and 802.11 and UMTS or LTE or LTE advanced? Why do we have all of this? Why not just one wireless standard that covers everything? Right? So that's a legitimate question, right? But the idea is that in each context, you have specific features and requirements that you need to fulfill, and you cannot do that using single standard. Never. Right? So in particular context, you need more data rates. You probably need no voice services, or probably you need mainly voice services but no data. But not only that, you need long range. Imagine مثلا submarines underwater, they communicate using Bluetooth. Bluetooth is done for very short range communication. But submarines, they can have thousands of kilometers, distance between them, and they need to have very long range communication. But we cannot مثلا use satellite communication for submarine communication. برضو that it doesn't work, right? So in each context, you have to have different features, different requirements, and that requires different set of standards altogether. And that comes from this slide. So the motivation is that, of course, we know that the wavelength is basically defined as what? If you have a simple مثلا sine wave, it has a specific time period, right? T. This is the period length, right? So wavelength here talks about the distance that this signal travels for a time T. Assuming that this signal travels into the air, what is the distance that this signal can travel in that T period? Okay? But since we talk about travel, this means we travel with a specific speed. Because we talk about electromagnetic wave traveling through the air, right? So if we need to measure the distance in time t, we have to know the speed. And usually the speed is a speed of light. Electromagnetic waves typically travel through the air using speed of light, right? So basically wavelength is time t multiplied by the speed of light. And we know that time t, the period, is actually 1 over f, right? So that's why the wavelength is c over f, okay? Which means that in any of these frequency ranges, you will notice the wavelength times the frequency is what? Is the speed of light. So lambda times f is always the speed of light. It's constant, which means that if you increase the wavelength, you reduce the frequency and the other way around. The multiplication of both is actually always constant. So when we talk about very low frequency ranges, 300 hertz, this is quite low. As we said, even our voice has 4 kilohertz bandwidth. And we talk about ultrasound, بيوصل 20 kilo hertz. Right, so 300 hertz, this is very, very low. In this very low frequency, right, of course, the wavelength is huge. We talk about the wavelength is 1 million meter. So imagine the span of the signal, 1 million meter. Okay, so the signal can take space in the air, huge space in the air, right? Type. What is the implication of this? The implication of this is that in very low frequency ranges, usually the signal has a lot more ability to penetrate, to travel through any medium, to travel through any obstacle, right? مثلا, if we have a very low frequency signal that travels in this classroom, all these obstacles, they will not affect the signal whatsoever. This is one. The other thing is that the range that these signals can go to, of course, naturally, is much more, right? So in very low frequency, the signal has better penetration through any obstacles. Like it can travel مثلا across the atmosphere. We know the atmosphere has like certain distinction or certain boundary, right? It will not affect the wireless signal. And that's why مثلا in satellite communication, they usually use low frequency. Because these low frequency signals, they penetrate through the atmosphere, they penetrate through any obstacle. It doesn't get affected, right? And that's a good physical property, right? And the range of communication is high. So the legitimate question is that, so why not use it? يعني احنا we can use, yes, we can use it for submarine communication. Why? Because the signal can penetrate through water. Even water does not affect the physical properties of the signal. It can travel for long distance even within water, which is good. What is the catch here بقى؟ حد عارف؟ Why don't we use low frequency communication all the time?
Cost, right?
Energy? يعني this is one factor, but this is not the main factor.
Still, poor data transmission.
Poor data transmission might be صح, might be لأن هو satellite communication it has طبعا lower data rates, but even this they can overcome low data transmission. The most important factor for low frequency communication is the length of the antenna, is the antenna size. The antenna size. We'll study that in a bit. 1 million meters, the antenna size needs to be lambda over 2. يعني if you have a wavelength of 1 million meters, you need to have an antenna 500 meters. So imagine the size of the antenna. And that's why we use it for submarine communication. Why? Because the submarines, they can have towers of antenna. Right? But can we use it مثلا for our phone? Never. We cannot do that. It's not feasible. In our phone, we have tens of these antennas, and each one is like this. Right? So we cannot do that. We cannot use low frequency communication. So it has its own physical property, which is يعني suitable for certain context of communication, but not in many applications. It's not feasible. ماشي? In satellite communication, yes. Submarine communication, yes. But in other types of communication, it's not possible. ماشي? طبعا when we talk about low frequency ranges, typically we talk about baseband communication طبعا. يعني because it's near the zero frequency component. And that's why here you see twisted pair coaxial. Why? Because these are wired guided medium. You know the coaxial, صح? In twisted pair and coaxial, we typically talk about a baseband communication, right? We talked about this because these are guided media, right? So the more we increase the frequency, right, we start to lose the ability of penetration. They start to have shorter range, right? And we start to have other physical properties that will affect the signal, like what? Like any small obstacle like this would cause reflections and refractions of the signal. And that causes يعني plenty of problems, multipath fading and issues, attenuation and so on and so forth. The penetration becomes not valid and so on. ماشي? But on the other side, we can have tiny little antennas for communication. We can have low power. We can use low power. ماشي? So يعني it's a trade-off, right? So that's why when we طبعا يعني مثلا كمثال AM and FM, right? FM مثلا works in the 88 megahertz range. In this range here, we can still talk about long range. It's long يعني not we're not talking about 100 kilometer مثلا like submarine communication, ولكن we're talking about hundreds of meters, right? So FM and AM, they talk about hundreds of meters of range, right? That's why مثلا radio channels, you drive your car around the city and you have seamless service. You still listen to the radio and there's no issue, right? Because the range is very, very wide. ماشي? And the antenna is a little bit smaller طبعا. Okay? Because here we're talking about 1 meter. So the يعني مثلا طبعا a little bit more than 1 meter, because here FM talks about 88 megahertz to 110 or something, 108, something like this. within that FM range you can divide it into بقى FM channels اللي هي الراديو channels that we listen to. Right. AM talks about much less than this. ماشي. So in that range usually you have wavelength of مثلا 10 meters or 20 meters, right? So you can have an antenna size of 10 meters or something like that. It's possible. So the FM radio stations is usually not tiny, but a little bit big. But because of this, the range is quite large. When we talk about بقى 2.4 gigahertz or 900 megahertz or 1 gigahertz or something like that, we start to talk about طبعا ايه? This is بقى the range of, they call it the millimeter wave. So less than this, we talk about 2.4 gigahertz or 1 gigahertz. We started to talk about مثلا 500 millimeters wavelength, which means that the antenna started to get very, very small. So on 2.4 gigahertz, the antenna is very, very small, right? So we can easily have MIMO. MIMO, you can have multiple antenna, and you can have massive MIMO. You can have tens or hundreds of these antenna on one device.
What is the MIMO?
MIMO اللي هي multiple input, multiple output. So you can have, we'll talk about this in a minute, where you have multiple antenna. So we'll see the advantage of having multiple antenna on one device or at the side of the workstation. We'll talk about this. So as we said, so the higher the frequency, the signal tend to penetrate much faster, much faster, and that's why the range is small. So Bluetooth, مثلا, for example, they are working the 2.4 gigahertz with low transmission power, so the range is quite small. We're talking about maximum 10 meters, maximum. ماشي? But the power consumption and the antenna size of the device is quite low, is quite small. ماشي? So in the 30 بقى gigahertz, we start to talk about إيه بقى? Signal that suffers a lot from obstacles. So the only way to have quality communication is to have line of sight. يعني the signal has to travel without any obstacles. You have to guarantee that the signal travels with no obstacles. اللي هو line of sight. Because if you dissipate the signal like this, it will reflect and it will have very low quality communication. Okay? So in 30 and 60 gigahertz, we have to talk about line of sight. And that's what makes the millimeter wave technology very hard to deploy. Because you have to have line of sight communication for devices to communicate, or a device with a base station. You have to have line of sight. Okay? Because in this range, the signal يعني suffers from يعني reflection and refraction and all of this. ماشي؟ واضح كده؟ So بقى in the visible light communication, we start to have بقى إيه more severe issues. When we talk about fiber optic communication, again in network 1 we talked about laser beams بقى, how the laser beams can travel again يعني line of sight and point to point. That's why we talked to you about the fact that if you bend the fiber optics, you cannot have communication. And if you want to have any kind of bends or something, you have to use mirrors and lots of issues. And that's why there is very big issue, a very big area of communication that started to evolve, which is called reconfigurable intelligence services, which is basically اللي هي RIS. I think we'll talk about this as well today. Yeah, Abdurrahman will touch on this today. Okay. So these physical properties, it has to be clear in your mind, because then you can answer questions like, مثلا, why don't we have low frequency communication for cellular communication? It will have larger range, and it will have better penetration, and I will not have to talk about multipath fading. I don't have to talk about this because the signal does not reflect from any obstacle. It penetrates anything. Right? But this is not possible. ماشي؟ طيب, these are طبعا يعني not by any means exhaustive list of the standards. You don't have to memorize all these standards. It's just a snapshot of some of the standards. the idea or the message taken from here is that the standard development, especially in the past, it was motivated by different types of systems, which affects the standards that gets developed in Europe versus US versus Japan versus. So there was standards that are going concurrent in Europe, in US, in Japan, and so on and so forth. So for example, we have GSM 880, and this refers again to the carrier frequency. And in the US, we have GSM 824. So in the US, they always need to have different standards. Even if they adopt some standards, they tweak it and they customize it for their market. Also, in the US, they tend to have lots of proprietary devices and proprietary technologies which is driven by the market, which is not necessarily standardized. But in a later stage, they started to believe and they started to develop standards, in many cases, حتى hand in hand with European standards. So, of course, again, we don't have to memorize these numbers. When we talk about cellular phones, here we have to distinguish the standards because the standard needs to have at least location identification. We need to have handover. We need to have roaming, things like that. When it comes to cordless phones, we don't have to have that. We don't need to have handover, right? Cordless phones, you know cordless phones, right? Yeah, phone sets with and the main set is like, it's like wireless يعني هو زي التليفون line عادي, but there's no wire. So I can take the phone and move around. But there is always a phone set. So even if I can move around, but the phone set is few meters away. And I cannot hand off from one phone set to another phone set. I don't need to do that, right? So I don't need handover. I don't need location determination. I don't need all these complexities. So the standards is different, requirements is different, but still wireless issues are there. And of course, here we're talking about short-range communication, not very, very long-range communication. Okay. So again, this is the carrier frequency. Again, it affects the antenna size. It affects this and that, which is similar. Cordless phones still use small antenna size and things like that. But again, we don't need to have handoff. We don't need to have very, very long range and so on. Wireless LANs, of course, the proliferation of wireless LANs emerged because of the data services, the fancy data services that they can provide. Of course, nowadays we started to have conversions when it comes to data services between cellular networks and Wi-Fi. And even data ranges, they started to get very, very close to each other. So cellular networks, they started to use packet switching, even sometimes for voice calls, right? So now you can have, some phones, they provide pure packet switching voice calls over the cellular network.
What's the advantage?
The advantage, again, is that it's better utilization for the operator. Why? Because in circuit switching, okay, the operator has to dedicate a full circuit for your call, whether you use it or not, right? So for the operator, the utilization is low because there is no guarantee that you will actually utilize 100% of this channel. But why do we do this? To guarantee quality of service, right? Because you will never have any voice disruption.
Exactly.
صح? So I can guarantee the quality of service for you, right? But the utilization from the operator side is very low, right? In packet switching, it's the other way around, right? The problem becomes that, can I guarantee service disruption? No, I cannot, because I can send a packet and the packet never reaches the other end. Because there is no dedicated circuit, واضح? I did not establish any circuit. But the utilization is high. صح? Because one packet will consume nothing from the network. صح كده? So this is the problem. But there's no guarantee that there's no service disruption. So it's a trade-off. So nowadays, we started to have a network which is extremely smart, right? So we, in such a case, that allows us to use packet switching, but at the same time provide some guarantees. This is what we call quality of service. ماشي؟ واضح? Any question? So again, this just shows a variety of standards. We don't have to memorize them. So the physical representation of any signal, right, relies on three fundamental parameters. Three fundamental parameters, of course. Normally, amplitude, frequency, and phase, right? So any signal, any sine wave, starting from مثلا here, right? It has a specific amplitude. This is the amplitude, lower A of t. The frequency here is A. This is the time domain, صح? This is the period length. So the frequency is A, is 1 over t, صح? This is the frequency, right? And the phase is actually A, this shift. This is the phase value. So if the signal starts at 0 time, at 0 value, we call that the phase is A, is 0 in that case. Phase is 0, right? Yeah, if the signal is like this, this signal has a 0 phase, right? So this is a simple sine wave. Why we talk about this simple sine wave? Because بقى ايه الحاج فورير has very nice theorem, right? Very nice theorem, very fundamental. Now what he said is really يعني changed the way we think about communication. What he said is that any signal on Earth, any irregular signal, whether it's sine wave, periodic, non-periodic, finite, any sign, any type of signal, analog, digital, anything, right? It can be represented using infinite sine waves with different amplitude, different frequency, and different phase. So any composite, we call it composite signal. ماشي? Any composite signal that has no regularity whatsoever, it's not periodic, ماشي? It can be represented using sine wave. The number of these sine waves differs بقى based على الايه؟ how composite and how complicated this signal is. ماشي؟ So a signal now can be classified in 4 different categories. The signal can be continuous in time or discrete in time. And it can be continuous in values or discrete in values. Okay? So, مثلا, so this signal is what is continuous in time and values, right? So it has infinite values and it has infinite values in the y-axis, right? This signal, it has infinite value in time, but it has discrete values in amplitude. Okay? صح كده? And this signal, even if it has infinite impulses like this, it may have infinite values in time, but the amplitude has a discrete values. واضح كده؟ ماشي كده؟ So you have بقى four different combinations. It has discrete values in time, discrete values in time, but the amplitude is continuous. So you have 4 combinations. So why do we distinguish between these 4 combinations? Why? Because Fourier said that if the signal has any discrete feature, it can be represented using finite number of sine waves. ماشي? That's this theorem. So a signal in general, يعني this signal can be switched using or can be represented using these 3 sine waves. ماشي? We call it harmonics. We talked about this in network 2, if you remember. مش طبعا. فاكر كلت امبارح. So in network 2 we talked about signal harmonics. But we said that this is a digital signal that has sharp edges, صح? And definitely it has infinite frequency components, right? But I can represent this signal approximately using only 3 sine waves. Okay? And as long as this signal is discrete, Fourier has this theorem that I can have finite numbers. So this is not necessarily infinite, right? If the signal is discrete, I can represent the signal using finite number of sine waves. واضح كده؟ طبعا this is very fundamental for us because it actually يعني gives us يعني the foundations how to deal with the harmonics of the signal, how to represent, how to have بقى approximate representation of the digital signals. Hence we can deal with it because the sine wave is the simplest form of a signal that has single frequency. The sine waves, this sine waves has what? Has in the if we talk about it in the frequency domain, sine wave has single frequency. So in the frequency domain, these 3 sine waves, they become like this. 3 impulses, that's it. Okay? So this signal in the time domain becomes 3 impulses in the frequency domain. So you can see how easy I can deal with this signal in the frequency domain, right? So I know about how to design a filter that filters this. Not only that, if I can do this harmonics, I can do some interleaving. I can have another signal here. Yani there is a lot I can do just by understanding the Fourier analysis of a signal in the frequency domain. Can do a lot with that. Okay. واضح كده؟ Any questions? So we know the fundamental parameters of characterizing any sine wave signal and how we can do that to even represent a composite signal using Fourier analysis. Of course, you have studied بقى Laplace بقى, we have studied Z transform وحاجات يعني ربنا يبعد الناس دي عنهم. Very complicated يعني. There are like some other transformations which is much more complicated than Fourier transformation. So this is what we said. A sine wave with the amplitude and phase. طبعا we have the time domain representation. طبعا we know that. In the frequency, it's very simple. A sine wave has one single frequency, so we can represent using one impulse, right? But we have another phase representation. معلش, this is new to them. Another phase representation. ماشي? We call it IQ diagram. We didn't talk about this. I think we touched on it in network 1, in network 2, right? But this phase representation also allows us to understand lots of characteristics about the signal. Very nice, especially when we talk about multiple symbols being transmitted at the same time for using modulation schemes. We'll talk about this. So this signal in the time domain is represented using one impulse in the frequency domain, which is represented using one point in the IQ diagram. This point, the distance to the 0 axis represents the amplitude. ماشي? And this angle represents the phase. Okay? That's it. We don't represent the frequency in the IQ diagram. Okay? That's why it's called phase diagram or IQ diagram. Why? Because we can actually have multi-user communication or using MAC layer, or we can design MAC layer based on the phase and not the frequency. Okay? So we can have some hardware circuits to distinguish between the signals based on the phase. And we can have multi-user based on the phase distinction, not based on the frequency. واضح كده؟ So that's pretty much it. I think we can stop here. So we talked about the most important thing here is that we talked about the physical properties of the wireless microwave signal in different frequency ranges. This is very important. And we talked about the basic parameters that characterize a wireless signal from the sine wave and Fourier analysis. And we said that we can represent a composite signal. A discrete composite signal can be represented using finite number of sine wave components. This is what Fourier has come up with. ماشي كده؟ طيب. We'll talk about the antenna next time, inshallah.